Hello everyone. In this lecture, we will give another application of the inclusion-exclusion principle, which is more advanced. We first start with some kind of combinatorial number theory. So we first define the Euler function. So by Euler function, we mean for a positive integer, define the Euler function phi by the formula. This is a number of integers among 1, 2, 3, 4, all the way to n that are relatively prime to n. It's a little bit abstract, but if you look at the example, it's very easy. For example, let's consider when n is 6. So how to compute phi 6? We first write down 6 numbers, 1, 2, 6, and then we delete all the integers contains a factor 2. And then we delete all the integers containing factor 3. The reason we only consider these two factors, 2 primes, is because 6 is 2 by 3. These two are primes. Okay, and the way we do that is actually called Sifu Method. Dates back to ancient Greeks, probably 2,000 years ago or more, like 4,000 years ago, 3,000 years ago. I can't remember exact number, but long time ago. And then remaining 2 integers, the remaining 2 integers are relatively prime to 6. In other words, they don't contain common factors with 6 greater than 1. Therefore, by the definition, you're actually counting the cardinality of the set containing 1 phi, so it's 2. And then a general question is, can we have a formula for general n? The answer is yes. And to do that, we just mimic what we did for the case we showed above. We first write down n as a product of primes. So that is P1 to N1, P2 to N2, Pk to Nk. So here we assume P1, P2, Pk, here k is greater than or equal to 1, are distinct primes. And Ni are positive integers for each I between 1 and k. And although it's trivial, but it's not trivial. We usually treat it as trivial. Is that this representation is unique. This holds for natural numbers, but when you enlarge natural number by some other element to a field, then there are problems, and this leads to more advanced course, which is called when it's not unique, then we lead to algebraic number theory. This is one of the two branches in the modern number theory research study. The other one is called the analytic number theory, which is more of complex analysis field. So if you are interested in this, if you're major in math or whatever, interested in this, you can look at my videos on YouTube for complex analysis course. Okay, I will not talk about more on this anymore. And then to compute this, you will see just in a moment, it's quite natural to apply the inclusion-exclusion principle. So first we define the subset AI as follows. It contains all the integer x such that x is between 1 and n. In other words, it's inside the ambient set, and the pi is not a factor of x. Okay, similarly, you can do this for all I between 1 and k. And after that, the phi n, okay, if you think it's too quick, actually here I omit one step, is define the whole set S to be 1, 2, 3, 4, all the way to n. But since it's trivial, so I omit this. And then, according to this definition, phi n, just the cardinality or the intersection of all the complements of AI. Okay, then let's compute the cardinality of 1 intersections, 2 intersections, and all the way up to k intersections. For 1 intersection, noted that A1, actually you can enumerate all the elements inside it. It's P1 to P1 all the way to n divided by P1 times P1. Notice that since P1 is a factor of n, this is an integer. This is an integer. Okay, therefore, what is cardinality of the set A1? Just n divided by P1. And similarly, A2, the cardinality of A2 is n divided by P2. AK, the cardinality of AK is n divided by PK. And now let's consider 2 intersections. Suppose you have AI1 intersect AI2. Then what you are doing is counting how many elements inside the set Pi1 times Pi2 times 1, Pi1 times Pi2 times 2, blah, blah, all the way to n divided by Pi1 times Pi2 times Pi1 times Pi2. Okay, therefore you just count the coefficient here is n divided by Pi1 times Pi2. And similarly, the last one for not last one, for an arbitrary intersection, you will have the formula for its cardinality. It's n divided by all the corresponding primes, the product of the corresponding primes. And if you plug in phi n, now here we apply the inclusion, exclusion principle yields that phi n is okay, let's rewrite. So it's a kinetic of the whole set minus the kinetic of one intersections plus the kinetic of, here's K, two intersections and minus blah blah. And then if you plug in, it's m minus summation n divided by pi plus n divided by pi1, pi2 plus n divided by pi1, pi2, pi3, blah blah. And if you factor out n, what do you have? It's 1 minus 1p, 1 over p1, 1 over p2, minus 1 over pk, plus 1 over p1 times p2, plus 1 over p1 times p3, plus 1 over p1 pk, plus 1 over p2 p3, and plus 1 over p2 p4, plus 1 over p2 pk, and plus blah blah, plus 1 over pk minus 1 pk, and then minus 1 over p1 p2 p3 minus, and the last one is plus minus 1 to k's power 1 over p1 p2 pk. Although here you have quite a lot of terms, but it turns out you can factor it which is exactly the product 1 over p1 times 1 over 1 minus 1 over p2 times 1 minus 1 over p3 times all the way to 1 minus 1 over pk. And therefore, we can conclude that phi n is exactly given by the formula n times the product for I from 1 to k, 1 minus 1 over pi. This is a quite nice formula. And an immediate application is phi 1 is 1, phi p is p minus 1 when p is a prime. So I just want to mention that in number theory, when they write down a variable p, they usually mean it's a prime. But in other fields, even in mathematics, you need to explicitly say it. So by that I mean, if you read a paper, they always use a p. And if you recognize that this is a number theory paper, just keep in mind, this probably just a prime instead of an arbitrary integer. For example, here, if p is not prime, it's definitely not correct. And if you have a power of p, then you will have this. Okay, so k greater than or equal. And a very important property of oral product is that they have the multiplication property. In other words, it's multiplicative. So for example, this is one of its form. So when mn are co-prime or relatively prime. In other words, they don't have any common factor greater than 1. Then the Euler function of Mn equals the Euler function of M times Euler function of N. So let's give a short proof. So suppose M is product Pi times Mi, P1 to Pk distinct. Okay, let's probably first write down all the other representation of N. And now we can see that here P1 to Pk and the P theta 1 to P theta L are distinct primes, and M1 to Mk, N1 to Nl are positive integers. Because here we use the assumption that Mn are relatively prime. Okay, then we can directly apply the previous formula that phi m just m times product for I from 1 to k, 1 minus 1 over pi. Phi n is n times product j from k to l, 1 minus 1 over pj theta. And for Mn, because here m times n should be product for I from 1 to k, Pi times product j from for j from 1 to l, Pj L and j. And since here Pi, Pj theta are distinct, so we can also apply the previous formula for m times n. So this will be m times n product for I from 1 to k, 1 minus 1 over pi, product j from 1 to k, 1 to l, 1 minus 1 over pj. And this is phi m times phi n. And a quick remark is that if Mn has a common factor greater than 1, then in general, this is not true. You can find an easy example. For example, phi p squared is p squared minus p. It's different from p minus 1 squared, which is phi p times phi p. This is because if you look back the proof, if Mn are not relatively prime, then this formula not in its reduced form. So because so here k Pik times j from 1 to l, Pjl theta l. This can be reduced to a simpler form if, for example, P1 equals P1 theta. You can combine the coefficients. Okay, so in this case, actually we have P times P. Okay, and then it's P squared. This P come from, okay, this P just come from M. This P comes from N. Okay, another remark, I don't want to write down the other remark, is that this Euler product is very important in modern number theory, especially in the representation theory, the long-length program, because later on people realize that not only integers has this formula, many functions and many representations can also be written as a product. So product. So instead of, so here may be an element. Instead of prime, so here may be some other functions. Pix, Pig. Okay, and they also estimate what is possible estimate for the function. Is it a polynomial? Or you have some gross estimate. If you are interested in this stuff, you can look at some representation theory, or just let me write down length program. You just search the Wikipedia for this. Okay, and now we look at another very interesting and elusive lemma for any positive integer. We actually have the following very interesting identity. N is a summation of all the phi d if d is a factor for all factors of n. Because why we guess this formula? Because we already know that phi n, not phi d. When d is n, phi n is less than n. So how to estimate phi n minus phi n? So firstly, if you don't have identity, you might guess, oh, probably this is bounded by some other numbers, for example, any factors, so guess n minus phi n is bounded by, this is a natural guess, all the information, for example, phi p1 plus phi p2, suppose n is a product of this form, plus all the way to phi pk. So you might guess, if this is true, and then it turns out not the case. Okay, and then you guess if you put in more, for example, or two factors, for example, p2 plus phi p1 p3 plus, and still not enough. Okay, later on you will see, okay, let's put everything in, and then you have the identity. So that's a very interesting guess how we develop this formula. But as soon as you have this formula, to prove it is not that hard. So first thing is, we rewrite the set 1, 2, 3, 4 to n as fractions. We divide everything by n. So 1 over n, 2 over n, blah, blah, n over n. And of course, some of you already noted that for the fractions, some of them are in their reduced form, some are not. Okay, and then we are going to just divide this set into, do some partition for this set. Before that, let's also write all the factors of n in this form. D1 less than D2 less than D3 less than Dm Di D1, D2 all the way to Dm are all factors of n. Okay, then let's look at the set we just constructed. So noted that each I over n can be reduced to its reduced form. What is a reduced form? That is, I over n is ai over bi, and ai, bi are co-prime. Okay, and another, okay, I will write here. Noted that here bi must be one of the factor of n, d1 dm. Therefore, you can write in this way. So first, you consider the element whose reduced form has a denominator 1. And then you consider all the fractions with a reduced form, whose reduced form has denominator d2. And how many how many fractions there are? So there are 5d2 5d2 fractions. This is by the definition of phi. Okay, similarly, you can write down all the fractions with denominator d3. Totally, you have 5d3 factors. And lastly, you have dm. So totally, you have 5d dm fractions. And if this is a partition, then you directly conclude the formula. So I leave it to you to check this is a partition. In other words, you need to prove that all the elements on the left side set 1 over n, 2 over n over n has its corresponding one on the right-hand side. And on the right-hand side, you don't have repetition. That means some elements correspond to 2 elements on the left-hand side. In other words, you need to prove it's a bijection. Okay, if we are satisfied with formula, then we are done with lecture. But usually people study because they are not satisfied with the result so far, or they feel like there's something must be done after that. So look at this formula. At least for my feeling is that I don't care about why n can be written down as something like summation of phi, because phi is more important to me. N is, I already know n, so I don't need to have some formula to represent it. So a natural question, or more natural question is, can we write down in the inverse form? That is, can we write down phi n as a summation of, for example, here some coefficients, and summation of m. So m is a factor of n. Okay, and if there's a, of course, there are many manually artificial ones. So the question is, can we have a natural representation at this, and how to figure out the coefficient? What is the coefficient? Okay, so this leads to a very interesting stuff called the Mobius inverse function, which is a very useful tool in combinatorics. So we first do this for subsets. Later on, we can generalize it to all the pole set or the set with partial orders. So for simplicity, let's denote the set 1, 2, 3, 4, all the way to n by xn, and denote pxn, define pxn as a set of all subsets of xn. This is well defined. If xn is some other set, probably you cannot talk about a set of all subsets. Okay, it's a finite, so everything is clear. Actually, this totally have two elements inside Pxn. Okay, and then we define a function. Sorry. So let's still use the inclusion as a partial order. So a partial order defined by containment. Okay, so for any function f from Pxn to R is a real number, or for any real valued function. We define G as follows. It's a summation of FL for all L contained in K. And if we define this for all K, for a subset K of Xn, then G is probably it's better to write in this way. Define a real valued function G from Pxn to R, to real number, by this. Okay. then the most important thing is then Fk is summation of all the summation for all subset of K of minus 1 to kinetic of K minus kinetic of L times GL for all K in Xn. You don't have idea why we do this, what's the motivation for this. So the idea is like this. If you look back to the previous example we have, so here F more or less some harder stuff, FD here, and the phi more or less some easy stuff N here. Oh, sorry. Oh, yes, in this way. And this is what we have, probably quite nature. And what we want to know actually is the inverse, how to rewrite F as a summation of G. So the result, we are going to prove at the end of this lecture. So here we just admit this. So the result tells you that, yes, we can do this in this situation. So F, just like here, can be written in this way. And what is the coefficient? So the coefficient, in this case, just 1 or -1, depending on the parity of the difference of cardinalities. Okay, and we first give some application. That is, suppose we have the star formula. Let's reduce the previous inclusion exclusion principle, and let A1, A2, all the way to AN be subsets of S, or S just Xn, and for a set K inside Xn or S, define Fk to be the number of elements of Xn that belong to exactly those sets AI with I not in K. So here the important thing is we have this exactly. Okay, that means we should have the elements, the elements we consider is a set. The set containing all the elements we consider is a intersection of AI, I not in K, and intersect AI complement let me write here. Intersect AI, I not in K, and intersect intersection of AJ, J in K complement. So this is exact, the Fk just a cardinality of this set. Okay, this is little bit complicated because as we dealt in the case of inclusion-exclusion principle, you have some extra conditions here. In reality, the more conditions you have, the more criteria you have, it's harder to estimate the numbers. And actually, the key point of the inclusion-exclusion principle is that you compute some complicated stuff as a combination of some easier stuff. Look back at the right-hand side of your formula of inclusion-exclusion principle. You have one intersection, two intersection, blah, blah, blah. And they are simpler than the one on the left-hand side. Okay, so the idea is also here. So FK is harder stuff. But of course, we have some easy stuff. Okay, and if we apply the previous scheme, then G, K, the function, then the function G defined by probably I don't use this wording. Just look at the GK. So the GK summation is a summation of FL for all L containing in K. This is by definition. So this function actually counts the number of elements O xn or OS that belong to all of the sets AJ with J not in K. Yeah, let's see, AI. That is GK is a coordinate of all the intersection of all AI for I not in K. And compare these two. Noted that the condition is condition on G on the set is has been weakened. So that's the purpose. Okay. And now the star, what star tells us? Star tells us you can compute the complicated stuff as a combination of the simpler stuff. You have this, and in particular, for the larger set Fxn, you will have this formula. And what is this formula? If you rewrite it, you will find it just formula for the coordinate of the intersection of all complements. And if you just split the whole summation on the right-hand side into, for example, into small sums depending on the coordinate j, then you will have this one. Coordinate is 0, -1, 0, and okay. I would rather write down the result. It's xm minus summation the one sum, one intersection plus two intersections. And the last one is -1 to nth power. Okay, and so we find that this is very useful formula. Then we would like to generalize it to any partial set. A finite partially ordered set. This is because although we have the same set xn and the same set pxn, all the subset which contains all the subsets of xn, but the partial order could be different. You can assign partial orders on that as soon as it satisfies the required condition. Okay, we would like to generalize this to some kind of inversion formula. So to do that, let's define Chi fxn be the collection of all real valued functions f from the Cartesian product, two Cartesian product of x to R with the property that fxy is 0 whenever x not less than or equal to y. So this means fxy different from 0 only if x is less than or equal to y. So you only assign non-trivial values for the function f when x has a condition, x is less than or equal to y. So why we define f? Because later on, all the functions we considered are contained in f. We narrow down the real functions to a subspace. So that's a usual way we do mathematics. First, you need to find a correct space. For example, if you want to solve PDE in a rigorous way, partial differential equation, in a rigorous way, you need to introduce some correct space, which is some are called subleft space, some are called Holder space. So in those spaces, you can have induction, you can have estimate, you can have the iteration, whatever. So you can have good stuff there. Outside those spaces, the theory becomes more and more complicated. Yeah, so mathematics, probably this is different from experiments or physicists. In mathematics, they always care about what we are considering. We need to narrow down to some correct way. And as soon as you have the correct formulation, correct wording, something quite trivial. Okay, and after that, we introduce operation on for all the functions in chi-f. So define the convolution product h equals f star j of two functions fj, fg in fx by summation for all elements in x, fxz times gzy, and for all xy. This is a little bit complicated if you haven't met this before, but it's quite a natural operation in mathematics. And I can give you some kind of pseudo-physics explanation, just like, so here you have source x, here you have target y, and how to compute h. So whatever, you have a lot of points inside it, and compute h, actually you need to consider all the paths, two-step paths. So the total infection from x to y, affection from x to y, is a summation of two-step, all the infections through the two-step path. So for example, this one, and let me use a different color. This one, this one, this one, this one. So you consider all the two paths, and for each two paths, you assign some basic stuff on it. So for example, this is z. Then here you assign this is not so clear. So let me change it to. Okay, so this is z. Then here you assign it fxz. Here you assign gzy. Okay, so the artificial explanation is like following. So affection from x to y equals summation all two-step paths and two-step paths x to z to y, and for first half of the path, you have x, z. This is the first affection, and then second affection is g, z, y. Okay, that's all I can explain. Okay. Then after you did the convolution, and immediately question is h still in fx? This is a crucial question, because whenever you talk about some operations between objects, you always want the object still stay in your space. Otherwise, outside space either means your operation is wrong or the space is not good enough. Whenever we talk about something, we always want that thing is still in the category we are talking about, we are referring to. Otherwise, you are just always referring to something unknown. It's not good. Okay, then let's check. The answer is yes. Check. Actually, you can just confirm that the above definition can be simplified in the following, as follows. When x is less than or equal to y, then the summation can be simplified to sum over all the triples x less than or equal to z less than or equal to y, fxz, gzy, because otherwise one of the two factors f and j must be 0. Okay, then otherwise you can confirm it's 0, and by definition h is in the space F. Okay, next we are going to show that this convolution operation is associative. Actually, for more general definition of convolution for functions, not on a finite set, you can still verify this, but the idea will be similar. So this is a general property of convolution. So let's denote the first one as L, the means left hand side. The second one as R, which means right hand side. And to prove it, you just write down carefully the convolution. So first you compute G star H. You first compute F star G star H. You first compute this star. So by the formula, you have this. Recall that here you don't use the second form. Don't use this one, because otherwise you will have more complicated form. You can try it. And next, we simplify the inside function. We try to write down the formula for this convolution. So there will be summation gzw times hwy. Okay, and probably all the fantastic in mathematics are done by the change the order. So, or in other words, someone said mathematics is just magic of changing order. Okay, so here if you change the order, you first sum z. And then sum w. Then we have is summation z in x fxz gzw and summation w in x hwy. Then what it is? Okay, this is just f star g xw hwy, and this is f star g star h, which is R. after we establish the abstract notion, then we introduce some key stuff. Remember, as I said, my feeling is that even if you have very good scheme, good abstraction, and a good definition, but always this is not the purpose. This is only a tool. The main purpose is how to organize your data. You should have some models in your mind, in your heart. This is what you really need to know. Don't spend all your time on the abstraction, then you will just be a tool man. Okay, just making tools for other people. You start with your own need to understand some models, then you establish the abstraction. Okay. So here, very interesting function inside the KLF X space is called the chronic delta functions. I guess at a chronic time, there's no notion of delta functions. This is only after Dirac. And Dirac's famous delta function. And mathematicians, Dirac is a physicist, and mathematicians spend probably a generation to understand what does Dirac delta function mean, because it's really not a function at all. Okay, and actually this is abusal the notation. It's not a function. It's actually, in mathematical sense, it's a distribution. Okay. But for the finite case, it's really a function, and we can see it clearly. If you have interest, you can search for the Dirac function and the distribution. This is a very important notion in PDE. Okay, and it's defined by assign 1 to x equals y for the pairs which are equal, and to 0 otherwise. Of course, you can first verify that this is in the KLF space. And most importantly, we have delta converse f equals f converse delta equals f for LF in KLFX. Or in other words, delta x as an identity function with respect to convolution product. Okay, so let's verify it. It's not hard. Yeah, I suggest you to do it by yourself as well. So by definition, this is just a summation for all z in x, delta xz, fzy. But by the property of delta, the only non-trivial value is when x equals z. So you can simplify this as delta xx fxy, which is fxy. And similarly, you can do the other f convolution f convolution delta. Okay, I will now repeat. Next important stuff is called the zeta function. yeah, the zeta function, I guess it probably has some interesting relation to number theory. Because in number theory, you have very famous Riemann zeta function. You have the Riemann hypothesis, which says, which locates all the non-trivial zeros of a Riemann zeta function. It's in some imaginary number line with a real part 1/2. But here, what we have is kind of easy. Probably it has a relation to the Riemann zeta function over finite field. And before we going on, I would like to make a remark. That is, given a pole set is the same as given a pole set is same as give a zeta function. Because from the zeta function, you can just decide what is the order between x and y. Okay. Example 3 is a little bit more complicated. That is, we're going to talk about construct some inverse of a given element and some condition. So suppose f is an arbitrary element of chi f in the space chi fx, and such that its diagonal is not 0. And then define G as follows. So first, GYY is 1 over FYY for all y in X. This is a diagonal, and then inductively define GXY to be negative 1 over YY summation x less than z less than or equal to z strictly less than y GXZ FZY x less than y and GXXY equals 0 if x not less than or equal to y. And here inductively, what does inductively mean? Recall that since we have finite set, then you can draw a Hessian diagram, for example, so that the lines means the order, partial order. They are partial order between them, and the above one is higher. Larger. The lower one is higher. So you start by this. We mean by inductively define. We mean that start with you can start with the minimal element, and they have a set, for example, x1. And then next step, consider the minimal elements of x2 defined by x, get rid of x1, and then consider the minimal elements. x3 equals x get rid of x1 union x2 and blah blah until the last one. Since we only have finite elements, you can complete the definition just in a finite step. Okay, then the most important thing is we can claim G converse convolution F is a delta function. So proof, this is because, so first noted that for delta XX or delta YY, by definition, you have, this is GXX dot, so I would like to write down more carefully. Summation x less than or equal to z less than or equal to x gxz fzx. The only possibility of z is x. Therefore, here you have gx x fx x. And by the definition, for the diagonal, you have this identity. Therefore, this is 1. Okay, now if you have xy and for x is not less than or equal to y, then if you look at the summation, then you find this is empty. You don't have any items to sum, so it's 0. And the last possibility is x strictly less than y. Then you will have these gxz fzy. Okay, and if you split this summation into 2 parts, you will have gxy times fyy plus summation gxz fzy. And for the first term, look at the definition here. That's why we define it in this way. Just like we can inductively solve the equation. I will just make a remark later. So you plug in the definition. This is negative g x less than or equal to z less than y gxz fzy plus positive fdy equals 0. And remark 1, what we do actually is inductively solve the equation G equals delta. G convolution F equals delta. So by inductively means GXZ FZY equals delta XY. You have plenty of equations to solve, and we organize in some order. That is, we arrange in this order x, y in, for example, lexicographic order. it's not exactly in this order, but if you look back the proof or the construction, you have this feeling. So you organize each single equations in this equation system in this way. And then we solved above, plug into the second one, plug into the third one, all the way down, solve all the equations. It turns out, and the condition Fyy is non-trivial, you can solve it. And the remark 2 is that, similarly, we can construct H for such F. So here such means diagonal non-vanishing. Diagonal is not zero. Okay, in other words, we have this one. And what is the relation between F and G and H? If we are in a number system, you might guess G and H are the same. And here, how to prove it? This actually is basic stuff in the abstract algebra course, the first few lectures. So recall that G is G convolution delta, and therefore you can write in this way. Delta is F convolution H, and by the associativity you have this, and you have delta convolution H, which is H, and then we call G the inverse function of F with respect to the convolution product. And the remark 3 is not every function in the Chi-F space has a inverse. This is easy to guess. If each element has an inverse, it's more like a division algebra or a field. And for example, Z, 0 in Z does not have an inverse. Okay, probably next time I would like to reserve the remaining part to next time. Next time we can discuss how to solve the previous inversion formula, that is we will prove okay, so I will stop here.